Hi everybody and welcome back. So this is example 11.2 in our uniform circular motion chapter. And this is actually kind of a practical application of, that is a real life relationship between the moon and the earth. So I'm going to go ahead and just draw this sort of at an angle right here. Earth in the middle. And the moon, we'll make the moon gray. I'll do it here and here as well. And the moon kind of going around the earth kind of like that. All right, so this is sort of like an oblique view of the moon going around the earth. Okay, so in reality, even if we were to look down on it straight down, the moon would not be going around the earth in a perfect circle. It's actually an ellipse, but it's close enough to a circle that we're going to pretend that it is. All right, so it's a very nearly circular orbit around the earth. It has a radius of about 384,000 kilometers. So let's go ahead and write that in. Our radius, and that's from there to there. Radius equals 384,000 kilometers. Well, of course, we need to convert that to meters. And if we move the decimal point over 3 more places, that would be 384 million meters. What I'm going to do is I'm going to write that in scientific notation. So 3.84 times, that would be 10 to the 8th meters. So if you write 384 million in scientific notation, that's what that would be. Okay? It also has a period of 27.3 days. That is a time period of 27.3 days that the moon takes to actually travel around the Earth one time. By the way, that's where we get our idea of our time span of a month from. A month is about 4 weeks, and that's where that comes from. By the way, a month comes from the word moon, so just a little earth science trivia there for you. So our time period, our time period equals 27.3 days, okay? Well, we can't use that unless it's converted to seconds, so we need to go ahead and change that. So 1 day is 24 hours, and 1 hour is 3,600 seconds. So we should be able to get, almost a full month in seconds. Okay, and I get, it's a big number too. 358,720 seconds. And I'm going to put that in scientific notation as well. So that would be an S right there. So that would be 2.36 times 10 to the 6th seconds. All right, so 2.3 million seconds per month, roughly, or actually a little bit more than that. Okay, so we have a radius and we have a time period right here. We want to find out what the acceleration of the moon is towards the Earth. Now, it's easy to think that if we're out here in space, that if we're beyond the atmosphere of the Earth, say you're in a rocket ship or something like that, all right, that there is no gravity. Well, there actually is. There's gravity. Gravity extends out virtually to infinity. And so what we're going to be calculating is that the acceleration, in fact, I probably shouldn't have drawn that right there, is the acceleration that the moon experiences towards the Earth. All right, even at that great distance, at 384,000 kilometers. All right, so that, what is that centripetal acceleration? Well, we have our radius, 3.84 times 10 to the 8th meters. We also have our time period, 2.36 days. All right, so what is our equation that we can use that involves those? Well, we have v squared over r, but that doesn't help us because we don't know the tangential velocity of the moon. But we also have 4 pi squared r over t squared. And that should help us out. We incidentally have a variety of this that deals with the frequency as well, but we don't have that. But this should work for us. Centripetal acceleration is 4 pi squared r over t squared. So 4 pi squared. Our radius is 3.84 times 10 to the 8th meters, all divided by our time squared. So that would be 2.36 times 10 to the 6th, that quantity squared, because the time period is squared. So what do we get? 4 pi squared, I should say, times 3.84 10 to the 8th, divided by 2.36 times 10 to the 6th, that quantity squared. And that should give us our final answer. And this is a really small number, 0.0027 meters per second squared. Or we could say that's 2.7 times 10 to the times 10 to the negative third meters per second squared. That's a very, very small acceleration. But it's enough of an acceleration to keep the moon trapped in orbit around the Earth. All right, so we know that as we go away from the Earth, gravity decreases. This distance away from the Earth, gravity is so little that it's a fraction of what we're used to here on Earth. But it's still there, and it's still enough to keep the moon in orbit around the Earth. So there we go, example 11.2. Hope that helps. Make sure you come see me if you have any questions. Thanks for watching. I'll see you on the next one.